Welcome, and this problem is inspired by the last problem we solved, and this is asking about the force of interaction between two halves of a sphere. And the problem says that we have a conducting ball of radius r and has a charge q. What force does any two halves of the ball, any of the two halves of the ball, exert on each other? This is the problem. And we have information that the surface of the sphere is subjected to a pressure from inside due to interaction of charges, and that pressure we already found equal to sigma square by 2 epsilon naught, where sigma is the surface charge density of the sphere, and that can be simply written as total charge on the sphere divided by its surface area, that is 4 pi r square. And now I'm going to consider an element of the sphere, and this element is going to be a ring of a small thickness on the surface of the sphere. You can see it here. This is the surface area. This is the elemental ring, and its surface area I'm going to take ds. Here are few forces df1 and df2 we were seeing in the picture. These are nothing but there are two symmetric points on this ring only, and on two symmetric points on this ring I have shown two forces df1 and df2, but I would better write it as dfi, because the points are everywhere on the ring, and every point of it same force is acting, and its magnitude is equal to dfi, so that if I add all these dfi's, I will get a force df if I simply sum them, and every two symmetric dfi gets cancelled out in one direction, that is this direction. This component dfi, the component of this dfi will be, I guess, df sine theta, because this angle is theta. You can see here in the picture, this angle I have taken it as theta. So this dfi sine theta gets cancelled out for spherical points, for symmetrical points, sorry, and only dfi cos thetas are getting added, and so that we will get the net force along the z axis, that is perpendicular to the plane of this ring, and the net force along z axis dfz will be summation of dfi cos theta, where cos theta is constant for each dfi, so that it will become simply summation of dfi multiplied by cos theta, and that you can write is df cos theta. Df simply summation of dfi is, I have already written it as df, so you can write it as df cos theta, and of course in this case the net force acting on the ring will be along the z axis, so I am going to write it as dfz, and this dfz is df cos theta. And now I am willing to find out the surface area of this ring, elementary ring. Of course, I guess the radius of this ring is simply r sine theta, because this length is r and this angle is theta, so its radius will be r sine theta, and its thickness, of course, you can write it in terms of theta as r d theta, so that ds will be the length of the ring, that is 2 pi r sine theta multiplied by its thickness, and that is r d theta, so that the total result will become ds. The value of ds will become 2 pi r square sine theta d theta. And we need to find the total force, and that is the Fz acting on one of the halves. This force is acting on one of the halves of the sphere and is produced by the other half, and this dfz is simply the summation of all dfz's acting on all those elemental rings of one half. And dfz we have written in terms of df and cos theta is simply df cos theta. What is this df? This df can be written from the previous solution in terms of pressure, like df by ds equals pressure at a point on the sphere, so that this thing can be placed here and df will become p ds cos theta, and the pressure, as we already discussed, is equal to sigma square by 2 epsilon naught, and ds from here you can write as 2 pi r square sine theta d theta, and there is a cos theta as well, so that we will need to integrate sigma square by epsilon naught pi r square sine theta cos theta d theta. And you can see from the picture, if you look at the picture, for one half you will get the limits from theta equals 0 to theta equals pi by 2, and one half of the sphere is covered within these limits. So you would like to put the limits from 0 to pi by 2 here, and you will obviously going to calculate this integration, because everything comes out except sine theta d cos theta d theta out of integration sign. And put the limits and solve it. I know how to solve it, and you obviously know, and the result you are going to get is sigma square pi r square divided by 2 epsilon naught. And if we put the value of sigma in terms of q, the result will become q square by 32 pi r square epsilon naught. And you can note one thing from here, that this force is simply this force on one half of the sphere by the other half simply comes out the pressure at the surface of the sphere multiplied by the projected area, because this thing pi r square is the projected area here, that one half projects at the equatorial plane of this sphere, and this projected area is pi r square. So you can remember this result as this is pressure multiplied by force on a part of a sphere by rest of the sphere is pressure at surface simply multiplied by the projected area by the surface at its equatorial plane part of the sphere. And this is simply written as pressure multiplied by projected area. Half sphere projects an area equal to pi r square, and if you take some other part of a sphere like this part, it will project an area like this. So you have to take it accordingly. Thank you very much for watching.